I was little, someone pointed out to me some constellations, but...
In this video, we're going to start by recalling some things that we talked about in the previous two lectures. So first, in lecture 21, video 2, we talked about two examples. So in one of them, let's say G is Sn, where n is at least 3, and H is the alternating group. So is this index 2 subgroup of Sn, and K is the cyclic subgroup generated by a transposition, let's say 1, 2. We saw that G was equal to HK, that everything in G can be written as something in H times something in K, that the intersection of these two subgroups is trivial, and that H is a normal subgroup of G. That's because H has index 2. All right, in the next example, we took GL2R, we let H be the subgroup SL2R, and K be the subgroup where you have a diagonal matrix with an X in the top left corner and a 1 in the lower right corner. So X is anything in R star. So in this way, it's easy to see that K is isomorphic to R star. So we saw that you could write G as HK, that anything in G is equal to something in H times something in K. It's clear that the intersection of these two subgroups is the identity matrix only, so the identity of G. And H is a normal subgroup in G because H is the kernel of this homomorphism that goes from GL2R to R star, that is, take the determinant of your matrix. All right, so in the last lecture, we saw the recognition theorem for semidirect products, which said if G was a group and H and K were subgroups in G, satisfying three things, G is equal to HK, the intersection of H and K is trivial, and H is a normal subgroup of G, then if you let phi be the function that takes K to an automorphism of H that is conjugation, so what does that mean? For any element little k in K, we define phi K applied to H to be KHK inverse. So phi K is this automorphism of H that we get from conjugating by K. Well, then this really is a homomorphism. And the map that takes H semidirect product K to G by taking the pair H comma K to the product HK is an isomorphism. So we proved that in the last lecture. And these examples are set up so that we can exactly apply this theorem as written. So what are we seeing in the first one? We are seeing that Sn is isomorphic to An semidirect product phi, the cyclic subgroup generated by 1 and 2, and GL2R is isomorphic to the semidirect product of SL2R and this subgroup that is isomorphic to, this subgroup that is isomorphic to R star, writing in the corner over here. Okay, so I'm going to pause and erase, and then we'll see a little more about this second example. In fact, this is just one instance in a more general way of understanding GL, the general linear group as a semidirect product. The last example we looked at was when G equals GL2R. But now let's let G be GLNR, and let's try to mimic this construction. So let's say H is SLNR. We know that H is a normal subgroup of G because it's the kernel of the determinant homomorphism. Let's now define K to be the subgroup of matrices of the form X in the upper left corner, 1s everywhere else along the diagonal, and 0s everywhere else. So diagonal matrices, X in the upper left corner, 1s along the diagonal after that, and 0s everywhere else. And X now can be anything in R star. So just as before, it's easy to see that K is isomorphic to R star. So if we take a matrix G in GLNR, we can decompose it as a product of something in H times something in K, just like we did in this GL2 example. So let's say the matrix G has determinant delta. Note that because G is in GLNR, delta is not 0. You can write G as G times the diagonal matrix with a delta inverse in the upper left corner and ones everywhere else. So determinant delta inverse. The product is 1. So this really is an SLNR. And then we multiply by the inverse of this matrix. So delta in the upper left corner, ones everywhere else, diagonal matrix. This is in K. So everything in G can be written as something in H times something in K. So G equals HK. Clearly, just from the definition of K, you can see that the only element in K of determinant 1 is the identity matrix. So is the n by n identity matrix. So what does this mean? GLNR is isomorphic to SLNR semidirect product R star, where the homomorphism phi is K acting on H by conjugation. So it's easy to check. I mean, if you just pick some matrix in SLNR, like your favorite one, and conjugate by some element of K, it's easy to check that this is not the trivial homomorphism. So what we've done is we've really written GLNR as a non-trivial semidirect product of SLNR and a subgroup isomorphic to R star. Okay, so I'm going to pause and erase and talk about another way to write GLNR as a product of two of its subgroups. We'll now show that when n is greater than 1 and is odd, GLNR is isomorphic to SLNR direct product R star. So what is the point here? Is we've seen that we can decompose GLNR as a non-trivial semidirect product of subgroups isomorphic to SLNR and to R star. And in this case that n greater than 1 is odd, we're also going to be able to decompose GLNR as a direct product of subgroups isomorphic to SLNR and to R star. So to make this work, the key idea is that the subgroups that we choose that are going to be isomorphic to R star, each one is isomorphic to R star, but they're different subgroups. So I think this is a really neat example because this is something that you might think is not possible at first, but it is. Okay, let's take G equals GLNR. Our subgroup H is going to be the same, is going to be SLNR. So H is still a normal subgroup in G. And we'll choose our other subgroup, we'll call Z, because it's going to be the center of GLNR. So now I claim that the center is the set of all matrices that are of the form some non-zero element of R star times the identity matrix. So it's going to be C, 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 C along the diagonal, where C is a non-zero real number. So this is a classic qualifying comprehensive exam type problem. So in the next video, I'll prove this claim for you, that this subgroup really is isomorph, or really is the center of GLNR. So the center of any group is normal in the group. So Z is a normal subgroup in G. So yeah, okay, so let's talk about the intersection of these two subgroups. What is the determinant of a scalar C times the identity matrix? Well, you get C's all along the diagonal, so you get C to the n. So now, if you want the determinant of such a thing to be 1, you need a real number, R, where R to the n equals 1. And if n is odd, the only one of those is 1. But if n is even, you could take C equals 1 or minus 1. So that tells us the intersection of these two subgroups. It's trivial if n is odd, and it's plus or minus the identity when n is even. So that's where this odd assumption comes from. Okay, so we can also see, just as before, that anything in G can be written as something in H times something in Z. So if the determinant of your matrix G, little g in G, is delta, then we can write G as something in H, G times this scalar matrix C times IN, where C is delta to the minus 1 over n. So you take 1 over the nth root of delta all along the diagonal, and then delta to the 1 over n times the identity matrix. So delta to the 1 over n all along the diagonal. And clearly this product is G, you just rearrange the parentheses. So what does that tell you? You can apply the recognition theorem for semidirect products and say, okay, well, now we know that G is isomorphic to H semidirect product Z, where that action, where the homomorphism phi comes from the action of Z on H by conjugation. But that action is trivial. I mean, if you take anything in the center, little z, and you take z, g, z inverse, that's always g, because z is in the center. So what does that tell you? That the homomorphism that you're using to define this semidirect product is trivial. So that semidirect product is isomorphic to a direct product. So what are we seeing is exactly this claim from the top that GLNR is isomorphic to the direct product H cross C. Alternatively, you can just use the recognition theorem for direct products. We have these two subgroups, H and Z, and they're both normal. G equals H times Z, and the intersection when n is odd is trivial. So G is isomorphic to a direct product of H and Z. All right, so in the next video, we'll prove the last piece of this argument, which is this claim about the center of GLNR.